Two of the most important words in this entire subject are linear combination and span, and they are simpler than they sound. A linear combination of vectors v1 through vk is just scaling each one by some number and adding the results together. That is c1 times v1 plus c2 times v2 and so on, up to ck times vk for some scalars c1 up to ck. So the real question becomes, can a target vector be built this way out of some other vectors we are given? Let's work a full example. Is b equal to the vector 1, 2, 3, a linear combination of v1 equal to the vector 1, 0, 1, and v2 equal to the vector 0, 1, 1? We want scalars c1 and c2 so that c1 times v1 plus c2 times v2 equals b. Writing this out, entry by entry gives three equations. C1 equals 1, C2 equals 2, and C1 plus C2 equals 3. The first two equations hand us the answer right away. C1 equals 1 and C2 equals 2. Now we check the third equation. Does 1 plus 2 equal 3? Yes, it does, so the system is consistent. So the answer is yes, B is a linear combination of V1 and V2, since B equals 1 times V1 plus 2 times v2. Now let's define span. The span of a set of vectors is the set of every single linear combination you could ever build from them, and it always turns out to be a subspace. First picture, span of the vectors 1, 0, and 0, 1 in the real numbers squared. This span is all of the real numbers squared, because any vector a, b can be written as a times 1, 0, plus b times 0, 1. Second picture, span of just the single vector 1, 2 in the real numbers squared. Here, c times the vector 1, 2 equals the vector c, 2c for every value of c. So the span is only the line y equals 2x passing through the origin. So two vectors that point in different directions can fill up the whole plane, while a single vector only ever sweeps out a line. Like and follow for more math tutorials, one idea at a time, nothing rushed.